We're going to have a go at the OCR January 10 question 4 from the M1 paper. Particles P and Q of masses 0.4 kilograms and 0.3 kilograms respectively are attached to the ends of a light inextensible string. The string passes over a smooth pulley and the sections of the string not in contact with the pulley are vertical. P rests in limiting equilibrium on the plane inclined at 60 degrees to the horizontal as it shows in the diagram. I part A. Calculate the components parallel and perpendicular to the plane of the contact force exerted by the plane on P. So we're looking at the particle P and we're asked for the contact force. Well, the contact force consists of the normal contact force, which is going to be R, and the friction force. If we look at the diagram, friction might be acting up or down. It's more likely to be acting up the plane, especially as P is going to be heavier. So P is 0.4 kilograms and Q is 0.3. So we're expecting P to want to move down the slope. So I'm going to draw friction going up the slope. Have we got enough information? So we've got a bit of a problem in that we don't know anything about the tension. So if I draw a picture of what's going on with P, here I've got my particle P, I've got 0.4 G acting vertically downwards, and I've got R perpendicular to the slope. I've got the tension acting vertically upwards, and I've got friction acting parallel to the slope. I've got three unknowns, which is just too many for me to work with. So let's see if I can find T first. How am I going to find T? Well, I'm going to find T by having a look at the particle Q. So Q's nice and simple to look at. We've got tension and we've got weight, which is 0.3 G. So I'm going to resolve upwards. We have tension must be equal to the weight. The reason it must be equal is because Q is in equilibrium, so it's not moving. Now I can add that tension onto my diagram for P. I can put 0.3 G onto my diagram. And now to find R and friction, it's just a case of resolving parallel and perpendicular. So I'm going to resolve parallel to find my friction. So I'm going to have all of my friction acting up the slope. The 0.3 G is going to be pulling me up the slope rather than into the slope. So I want plus 0.3 G from my tension. But now I need to decide whether it's going to be cos or sine. Sine 60. And then I need to take away the 0.4 G because that's trying to pull me into the slope. And is that going to be cos or sine 60? Make the angle 0. I don't want it, so it's going to be sine 60. And this is equal to 0. Obviously, when you're doing it, you're going to space out your work a little bit better than me. And now I can just put this into my calculator and it comes out as friction being 4.8487 newtons. Now, we're likely to want this number again, so I'm going to store that in my calculator as A. And then to find what the normal reaction is, I'm going to resolve perpendicular. So I'm going to have all of my normal reaction, and then if we have a look back at our picture, you can see that the 0.3 G is going to be pulling me slightly away from the plane. So that wants to be positive, plus 0.3 G, and it's going to be cos 60 because we're resolving in the other direction. The friction's not going to be acting because it's perpendicular to the direction we're looking at, and then I need 0.4 G, and again that's going to be minus because it's pulling me into the slope, and it's going to be cos 60. And again, we're in equilibrium, so it's going to be equal to 0, and I can just work out what R is going to be. And I get R as being 0.49. Part B asks us to find the coefficient of friction between P and the plane. We know that because P rests in limiting equilibrium, then friction must be at its maximum, so we can say that the maximum value of friction must be equal to mu times R. So we get our 0.8487 equals mu, which is what we're looking for, times our 0.49, and we just divide them. I get mu as being 1.73, which is a very big value for mu. Then we're told P is held stationary and the particle of mass 0.2 kilograms is attached to Q with a string taut. P is released from rest. So Q before was 0.3 kilograms. Now because we've added on an extra 0.2 kilograms, Q now has 0.5 G of weight. P is still 0.4 G in terms of my weight. And then it asks us to calculate the tension in the string and the acceleration for particles. Now, because it's going to start moving, P is going to leave the surface and we can forget the contact forces that we found before. This becomes a normal pulley question. So we're going to have our Q going downwards and we're going to have our P going upwards. And P is being pulled upwards by the tension and it's got a weight of 0.4 G going downwards. And Q is being pulled downwards by 0.5 G and tension's slowing it down. So I'm going to form some simultaneous equations by resolving vertically. So I'm going to end up saying T minus 0.4 G is equal to the mass times the acceleration, so 0.4 times A, because it's not in equilibrium. And when I look at Q, I'm going to get 0.5 G minus T, and that's going to be equal to 0.5 A. And then because we've got 1t in each equation, we can just add our equations. We'll get 0.1 G, and that is equal to 0.9 A. So I can say A is equal to 0.1 G divided by 0.9. So I get A as being 1.09 to three significant figures. And then to find T, I just substitute that back into one of my earlier equations. I get my tension as being 4.36 newtons. And that's the end of the question.